In this video, I want to just go quickly through the basic algebra or arithmetic of power series and how you can combine them by adding, subtracting, multiplying, dividing, and then even doing some calculus. So here we go. Suppose I've got two power series. So f of x, I'm going to have the sum n equals 0 to infinity of an x minus x0 to the n, and g is the same except that I have b n's here instead of a n's, right? So they're both power series, potentially different coefficients in front of the powers of x minus x0. Okay. And I also want to assume that both of them are convergent within the interval from x0 minus r to x0 plus r for some non-zero r. It's possible that each one of these has a different interval of convergence, but they both be centered at x0. So take the smaller one, and then you know in the smaller one they're both convergent. So if you're within the interval of convergence of both of those, then we can do this. So for x in this interval of convergence, then this says we can add the two power series by adding corresponding coefficients. Essentially, you're adding like terms. Add the constants together, add the linear parts together, add the quadratic parts together, and so on. But you can just add them term by term. And likewise for subtracting, you can subtract term by term. In fact, in the last video, or maybe two videos ago, let me go up to it, when I was finding the value of the sum of a geometric series, I said, let's multiply by r. Actually, I haven't mentioned that I can do this distributive property yet. That's next on my list. I can distribute that r through, and then I said I want to take this one and subtract that one. So what I'm doing is I'm essentially thinking of this as a power series. Instead of x as my variable, r is my variable. And I said, okay, well I can subtract the constants, c minus 0, I can subtract the linear parts, I can subtract the quadratic parts, I can subtract the cubic parts, and all of them disappeared except for the constant term right there. Now, that subtraction is happening within the interval of convergence. If I'm outside the interval of convergence, then that whole thing made no sense. Right? Notice in that part of what is happening here is it's saying you can rearrange, if you're within the interval of convergence, you can rearrange the order that you add them up in. By definition, we're adding the first one plus the second one plus the third one, right? And we're taking partial sums and then looking at the limit as we get more and more things in our partial sum, right? But if you rearrange things, then the partial sums will be different. The question is, rearranging them, does that change the value of the sum? And the answer is no, if you're within the interval of convergence, right? If you're not within the interval of convergence, so let me find an example of that. So when we were talking about the alternating series there, we mentioned this, what's this called? The alternating harmonic series, right? This converged conditionally, as it turns out. And it converges, it adds up to log 2. But if you allow me to change the order of them, I can get this to add up to anything you want. I can get it to add up to any positive number, any negative number. I could even get it to add up to infinity if you wanted me to. Okay, if you allowed me to change the order of adding here. Okay. I'm not going to explain that in this video, but the thing is, changing the order of an infinite sum only works when you're in the interval of convergence. And so if you happen to be wandering around YouTube and you run across a video or two, or whatever, of someone claiming that the sum of 1 plus 2 plus 3 plus 4 plus 5 plus and so on, the sum of all the positive integers, is equal to negative 1/12, be highly suspicious. They give a proof. There's this one website or YouTube channel that actually does really good math stuff usually, but they have this one that's like, what? They essentially do exactly what I did with taking one sum, one thing, and adding on another power series, term by term, saying, hey, look, I can do this one plus that one. But each of them is not within the interval of convergence. The two power series that they're adding are both outside of their interval of convergence, and so when they add them or subtract them, whatever they do, all bets are off. There's no possible way that they can accurately say that this is the answer, because those sums could add up to anything. You could rearrange the order. You could, if you're allowing that to happen outside of the interval of convergence, then you could get the answer to be anything you want. So if it can be anything you want, be highly suspicious of the one they got. So anyway, the sum 1 plus 2 plus 3 plus 4 plus 5 and so on is not equal to minus 1/12, even if they claim physics is using it. And if physics is using it, then there's really something wrong with physics. All right, so back to the new stuff here. You can add term by term, you can subtract term by term. And as we saw in the example up above there, if you take your power series and multiply by a constant, there's essentially a distributive property, and you can distribute that constant in. This is okay when you're within the interval of convergence. Now, we can also multiply the two complex numbers together in the following way. So the product of those two things is going to be this new power series, where the coefficients here are given by this formula here. It looks a little crazy, but let me write it out and we can see where this comes from. Okay. Essentially, multiplying power series together is like multiplying polynomials, which you use by FOIL or big FOIL, right? And this is really big FOIL. They got an infinite polynomial times an infinite polynomial. And so what we do is we say, okay, this A0 has got to be multiplied by everything, and the A1x has got to be multiplied by everything, and so on. And then let's collect like terms. So let's just collect like terms from the start. The only way I'm going to get a constant here is the constant from this one times the constant from that one. That's the A0, B0. However, to get a linear term, I give two ways to do it, because I could do the A0 times B1x, or I could do the A1x times B0. And so I get this thing. To get a quadratic term, you could do it three ways. The constant times the quadratic, a linear times a linear, or a quadratic times a constant, right? So these are the possibilities. Now notice that what this is here, this is the Cn up here, this would be with n equals 2. So this is the sum I equals 1 to 2 of ai b2 minus I. So with I equals 0, this would be a0 b2, it's this one. With I equals 1, that would be a1 b1, that's this one. And with I equal to 2, this would be a2 b0, and that's this one. So that gives you the three terms, the three products that would be used to get the coefficient of the x squared. Likewise, you could do the same thing for the x cubed, the x to the fourth, and so on. So you're essentially multiplying power series like you would multiply polynomials. Okay. In each of the cases that we've looked at so far, adding, subtracting, multiplying by a constant, and multiplying power series together, the interval of convergence of the result is the same as the interval of convergence of what you started with. Division we can also do, but it's not as straightforward. We can actually essentially do polynomial really long division. Right? That you divide a polynomial by another. There's a method for doing that. We could do it with these infinite ones as well. It's hard to write down what the result would be based on knowing what you started with. I mean, you have to do some examples, right? One of the issues, though, with this division is that the interval of convergence may change. It could get smaller. Because if you're in a spot where g of x is equal to 0, then you're going to be creating an asymptote in the function itself. And so the interval of convergence would not be able to cross over that, that asymptote. And so you could have a shorter interval of convergence. However, within that shorter interval of convergence, you can do the division just as you would divide polynomials. Now, let's finish this off with some calculus. That we can take derivatives and integrals of power series just as you would expect, because they look like infinite polynomials. They look like these big long polynomials, and you would take a derivative just like you would do a polynomial. So the derivative here I don't actually like it written out like this, but remember f was, well, I'm thinking of f like this, a0 plus a1x plus a2x squared and so on. And when I take the derivative of that, the derivative of the constant goes away. So I should have a constant to start with, a1, and then 2a2x, that's there, and the next one would be 3a3x squared and 4a4x cubed and so on. That's what this is saying, n times x minus x0 to the n minus 1. This would be the derivative of the power series. Likewise, you can integrate by integrating term by term. So increase the power by 1 and divide by that new power, plus a constant, of course. So there's a constant here. The a0 would go to an a0x, right? The a1x would go to an a1x squared over 2, and a cubed, sorry, then the a2x squared would be an a2x cubed over 3, and so on. And you can just integrate term by term. And remarkably, in both the differentiation and the integration case, the interval of convergence is the same as the function you started with. And we will use this substantially in what we do in solving differential equations next week.